I need to set myself as a.
Hello everyone, good evening. My name is Anshu chhetri and my teammates' name are Neel and Pranavi. Today we're presenting new D-RaNGe. This was originally presented on 25th IEEE International Symposium of HPCA. Here we're using community DRAM devices to generate two random numbers with high throughput and low latency. So we are a very obedient student, all of us. We follow our professor's footsteps. So every engagement gets reward with a treat. So what is the first thing that comes to your mind when you hear the word random? Something that's unpredictable, right? Something that we cannot guess. So now imagine one scenario. You're standing in front of a classroom and there's a ball in front of you with lists of name from everybody in the classroom. So we have to wear a blindfold and just pick one of that. And whoever name pops up wins a prize. And now we follow the same scenario, but this time we follow a function with a random function where it gives a random name from the array where all the name of the students are written, and it gives the output and the same result is there. The winners get some prize. Which one of these two would be a true random? Something, even we start from a same point, int at the same point, we know exactly what's going on behind the scenes, and still the results are unpredictable. Which one of these two would be truly random? Yeah, that's true. So the one kind of numbers that we do know the algorithm behind is known as pseudo-random numbers. Here we use a deterministic algorithm from a starting point called SEED, and we generate numbers that might appear as random, but they do repeat itself in some instance. So other number is true random numbers. These follows a non-deterministic physical entropy source. So the numbers that are generated are truly unpredictable. Even though we do know the number that generated before, still the outcome is we don't know. So these both exist out in the real world, so they have their own importance. Pseudo-random numbers, it is fast and cost efficient. So if there is a scene where generating true randomness is not the most essential point, then we can use it, like for example, while we're playing video games, where generating fast bits are more important than the randomness. And other is true random number, though it is not as fast as pseudo and it is costlier, and sometimes it occurs unpredictable failures. That is why we require some intensive testing. Where the security is the most essential point, we use this kind of numbers there. So what are the essential points that we should keep in mind while talking about random numbers? First thing is entropy source. So there should be a the physical origin of randomness. Like for the example, we saw the ball was the entropy source and the person who was extracting that chit was a process. So the entropy source should always be uncontrollable and it should be isolated from the external interference. Second is the extraction technique of the randomness. So the entropy source cannot be modified, and also the physical randomness that we get, we should be able to generate into digital bits. And that should also be through high throughput and low latency. And sometimes bias removable, because sometimes we introduce some correlations like or more ones or more zeros. So this is an optional step. If a parrot is reading one of your fortune cards and they tell you you're going to be millionaire one day, is it truly random or is it not? We don't know the answer. So for the executive summary, motivation behind is that high throughput random numbers enable system security and randomized algorithms. Many systems like IoT devices or mobile systems or some embedded systems, they do not have an additional hardware for this kind of things. So, but they do have DRAM devices. The problem behind the current DRAM-based TRNG is that they do not provide a fully deterministic, non-deterministic entropy source, or sometimes they do not provide high throughput data. The goal behind is that a novel and effective TRNG we can achieve with high throughput, low latency, and there should be no adverse effect on the concurrently running applications in the system. And takeaways would be high throughput TRNGs, we've achieved them with low latency, and there is no additional hardware modifications. Some of the real world examples or some of the needs for the true random numbers are in cryptographic systems where we use encryption and decryption. The text, something like I'll meet you at the church, will look something like this if you encrypt it. And the need for true random numbers is the key, because it is the most essential point in cryptography to encrypt and decrypt the systems. So the key should be truly random. This is the most essential point. And also in lottery system, how unbiased it will be if somebody who knows behind the scene what's going on and can generate the lottery winning numbers, and others people, it will be very unfair to others, right? So also in one-time passwords, where nowadays we use it in every place. So it is also very essential for our security for it to be truly random. And also we use it in health and scientific testing to remove some of the biases. So some of the products that are out in the market is a pen drive here. We are known, it is a true random number generator. And also the thing with telepathy, maybe the parrot was right. We also use it for telepathy. So some of the example of entropy sources, one can be clock jitter. So clock jitter is when we access packets from a network through a channel. Example, we are playing a video, we're streaming a video, and the video gets loaded, and there is a buffer in front of it. Like it goes the flow, and sometimes the network is not good, we get some delays between, and it reloads and this loads again. So it means the bit did not reach the destination in the time. So this difference, when the bit should have reached the destination, but actual time when it did reach, it is called clock jitter, and this is completely unpredictable because it depends on the things like network congestion, the packet loss, and other factors. So this is also one of the source for the entropy for true random number generations. There is user timing input parameters. So every user is different, and we have different how we use the keyboard, how we use the mouse or the touchpad. So this is also one of the source for the entropy. Now, why DRAM? What can be one of the things we can think of while using DRAM as an entropy source for true random generation? What will happen if we read too fast from DRAM? What will happen? Yeah. If we read too fast from the DRAM, what will happen? If we read too fast from a DRAM, what might occur? If we make too many requests and read too fast from a DRAM? Failures?
Might read wrong data.
That is also one of the point, one of the idea that can be used DRAM for. But why DRAM? The other entropy source does exist in the real world. So why are we using DRAM instead? So DRAM devices provide an interface capable of transferring data continuously with high throughput. And the most essential part is it is present in almost every device. So we use IoT devices a lot these days, and they are small and dedicated. So additional hardware for just true random is not possible. But DRAM is present in every device. So this is the most essential point why we're using DRAM instead.
So let's start by recalling our understanding on DRAM hierarchy and organization. So at first we have, next. At first we have D-RaNGe. It contains DRAM chips. Like chips contains 4 to 8 banks, and banks are made up of matrices or subarrays. They are made up of like DRAM cells, which are connected in a row architecture called DRAM row word line, and which are connected to the column architecture as bit line. So when an activate command comes to the DRAM bank, first it decodes the row, and then it amplifies it and stores it in the row buffer. So from where we can read the values of the specific DRAM row that is activated, and yeah, that's how a DRAM read operation works in this. Next. So to visualize the DRAM operation read or write, let's take an example of DRAM read. So the bit lines have sense amplifiers. So do anyone remember what is the initial voltage of the bit line? Yes, correct. It's half voltage. So when an activate command is there, next one. Yeah, so DRAM contains the data. Next. So when an activate command reaches the DRAM subarray, it first activates the row. Then it connects with the bit line, it amplifies the voltage, and then it stores it in the row buffer. Next. So from here, we can operate a read or write operation from the row buffer. But when we try to read from another row, we first need to pre-charge the current row. So in this, this first clears the current row, which closes the current open row, and then it makes space for the next row to be read. Then we have one more activate command, so which activates the second row. Then it amplifies the bits and it stores the values in the row buffer, from where we can do the next read or write operation. So this is the chronological order. First we activate, then we pre-charge the current row, then we activate, and then we can perform a read operation. Next. So here, to understand the D-RaNGe, which is we are using DRAM to operate to generate the truly random number. So based on this image, we are reducing the time parameter to read from the local row buffer. So that's how it creates bit error. So it creates randomness. So let's take one example to clearly understand why we are using the DRAM time parameter. Next. Okay, so if everyone is trying to jump and cross a certain line, next. If there is line which is 2 below, then everyone would be able to like cross that line. But when everyone is trying, if we are increasing the height of the line, then only somebody will be able to cross that line. So this is creating partial randomness, and it's unpredictable, like who is gonna clear that line and who is not. So the same scenario comes to the DRAM cells. So when we decrease the timing parameter to read the voltage from the cell, some cell might have the like high voltage, so they can cross it to the readable voltage, and some cells might not reach to the readable voltage, that creates the randomness. Next. Oh, previous one. Previous. Okay. From this image, it is not too difficult to understand what is the timing parameter, but we have one scenario which will be easy for you to visualize the timing parameter that is occurring in this process. Next. So in the memory controller, does anybody remember what are the 3 channels that are transmitted in the memory controller? The 3 channels in the memory controller. Address bus.
Data control.
If you name 3, you will get the chocolate.
Address, data, and control.
Data bus. And third. The command or instructions. Yeah, control command. Okay, so here we are talking about the address bus. So there are row address buffer and column address buffer. First, it decodes the current row, then the column. So can you click on the next one? Okay, so RAS is row access strobe, which tells the sense amplifier to select which row we have to activate and store it in the row buffer. And the CAS is the column access strobe, which selects which column we have to perform the read or write operation. So click on next. So this delay is called row to column access delay. First, it defines the row, which row we have to activate, then at which column we have to perform that operation. So this is called row to access delay. So when an activate command reaches the memory controller, the subarray, first we receive the row address strobe. Click next. Okay. So when it reaches the row access row address, this you can count it as the propagation delay for the row address buffer to decode the current row. Next, we receive the column address. Here we have to, here the column decoder, the multiplexer or demultiplexer, it defines which column we have to perform that. And the time it takes, it can be considered as the propagation delay for column multiplexer, demultiplexer. Then back. When the row access strobe finishes, the data becomes available to the row buffer. So after that, we receive the column address strobe, and the data will be staying in the row buffer until the CAS, until the column access strobe. So which defines on which column we have to perform that read or write operation. Next. Okay. So after this time, if we perform any read or write operation, that would be correct on the row buffer. Click next. One more next. Okay. So this time is called row to column delay, that is TRCD. Next. Okay. So if we consider separate DRAM cells, they don't have the similar voltage and they have probability, like some cells will be amplified very easily, and some cells which have less voltage, they might not reach to a readable voltage from the row buffer that we are performing an read or write operation. So when the activate commands comes to the sense amplifier, it amplifies the voltage to the row buffer until a readable voltage. But there is V minimum voltage at which if we read the voltage, then that also will be enough to like read from the row buffer. So if we try to read from the minimum voltage, there might be some cells that won't qualify for that V minimum voltage. So these cells are like weak cells. They create the randomness. They induce the bit error, and this probability is called as like passing probability to the V minimum voltage. So if we are in the paper, then the TRCD, initial TRCD is around 18 nanosecond, and they have tried to reduce it around 45 to 50%. So if we read it around 45%, then only some cells will be able to pass it to the readable voltage, and that induces the randomness. Next.
Cells latency.
Hello, can you hear me? Hello.
So each DRAM bank can only activate one row at a time. To maximize the throughput, we alternate the rows in each bank. So we choose the rows with high RNG rich cache line. we reserve the neighboring rows to minimize DRAM read interference. And the quick alternation allows the overlap axis. While one row is being pre-charged, the next row in the same bank can be activated. The DRAM reserves those specific cache lines for RNG generations, and these reserved lines are never touched by other systems. So these isolations avoid the data corruption and the interference from the other systems.
So here we'll be starting how well does the D-RaNGe really work. For that, we are going to have the evaluation, and the evaluation is done on three key aspects. The three key aspects are the randomness quality, which is done by the NIST statistical test suite. And the second one is RNG cell distribution, which is analyzed by the density. And the TRNG characteristics, we have like six key properties for that. So the parameters that were tested are the manufacturers and the increase in the temperature and the 15 days. The test was done for 15 days. So here for test for randomness, we have used the NIST test, which has 15 rigorous tests that were done, and it passed all of the tests. The goal was to see if the generated sequence is indistinguishable from the truly random one. And there we have to include in the test that if the outputs has entire bits of ones and zeros, and if the output is unbiased with the similar segments of bit streams, and then we have the limited number of uninterrupted sequence of identical bits. That means that if we have the uninterrupted sequences, it's within the range acceptable that is already tested by them. And the alpha was chosen like 0.001, and the tests have passed all the 15 tests, the p-value. And then comes the RNG cell distribution. It has three aspects, that is like function of generation. It was intentionally, it's like the random bits are generated by intentionally accessing the DRAM cells with a reduced activation latency, and then the sense amplifier is turned in its metastable state, which gives a 50% probability of the failure probability. And then comes the density. When we use the density as throughput multiplier, which is like the DRAM is accessed at the granularity of DRAM words, which is typically of 30 to 64 bits. And the most DRAM cells, when we have the more range of DRAM cells, it generates the most random bits per memory access. And then the key findings of density is that the RNG cells are widely available in every tested DRAM bank, and every analyzed bank had at least one, had multiple words of at least one RNG cell. We had the throughput as 4 times increased when compared to the other works of the DRAM. Here are the prior works. Here are the prior works of the DRAM based on TRNGs. Here they have used the command scheduling. We can here do first we generate many concurrent DRAM requests. Then we have it sent to the the memory controller schedules the request, and then they measure the delay in the request completion, and then they convert timing jitters into random bits. That's how the command scheduling works. So can you guys guess why this is not a better approach when compared to D-RaNGe? What might be the disadvantages of using this apart from D-RaNGe?
Command inputs are also unpredictable. Why it cannot be done?
We already discussed that a lot of times, and the paper title was that too, if you want to hint. That was paper's title, basically.
Waits until all the requests finish.
So let's go ahead. It's like the physical entropy. If we enforce some recent AI techniques or deep learning onto the system, the attacker can know the memory traffic and understand what the bits are, and he can predict the things. So it's not possible to use it, and it will have the low throughput, and then it will also have it will be also dependent on the workload and controller design. The second one is the DRAM data retention. Data retention is all about the amount of time that a DRAM cell can safely retain the data without being refreshed. And If the voltage drops too low before the next refresh, the cell forgets a bit, and that leads to retention failure. And how if we disable the refresh temporarily and wait for the short time and then read the data, we can get some bits flipped due to the charge loss. And can you guys guess here if what's the drawback for this one to not to be used? Because if we are waiting for some time to refresh the data temporarily, what would be the thing that why we are not using this? Yeah, time delay. That's right. So it's like the latency for generating random number is too high, and there's a time delay. And then it comes for the DRAM startup values. When the DRAM is powered on, each cell is started on an undefined electrical state. This is unpredictable initialization can be used to generate random bits. That might be also an entropy source for that. The problems here are like it requires complete power cycling, which cannot generate random numbers continuously. That might be a problem for that. And then it's slow and impractical, and it might be not truly deterministic, it's partially deterministic. And then we have compared the other papers with the D-RaNGe one. The D-RaNGe had the latency as 100 nanoseconds to 960 nanoseconds, and the energy consumption was 4.4. And then the peak throughput was 717.4 MB per second. So you can see here that the latency for other papers is like pretty less, and then the peak throughput is here also it's less. For the D-RaNGe, it's like 717.4 MB per second, and that's the highest one for that. Next. And for strengths and weakness, the strengths were that the D-RaNGe could satisfy all the 6 TRNG effective characteristics that are high throughput, low latency, and other things. The performance is that the random numbers generated in memory are like not in that, like it's a software based, so it's not in more communication with the CPU. And the security is the tasks stay inside the DRAM, so there are like fewer input-output leaks that leads to like we can be sure that there will be no row hammer attacks or some other kind of attacks that were earlier there on the other prior works. The weakness is that memory controller access dependency here. There is a there is a dependency on the memory controller for every regeneration, so it's a bit it's a bit an issue when we like start the generation of 2 random numbers again and again. So that's a weakness over there. And it has like high overhead of RNG cell identification or profiling. And the test was only done for like 15 days, which was like they characterized the test for like 15 days. After the 15 days, the aging effect of the cells is not stated. So that's a drawback too. The critiques is that the same authors have written another paper on like in 2021, in which they introduced the 4-row activation in the DRAM, and they had the latency of like in GBs per second instead of like the MB per second in this paper. So that was the next thing for the authors to be given. The future work is that we can produce some like alternative timing parameters like TRS or TRP. Like it can increase the multiple entropy source for us, and even we can integrate it with the PIM, that is processing in memory. And we can even have a development of standardized secure memory controller abstraction layer. These all are like just hypothetical situations where we can increase the entropy sources or like induce something into the thing that was already written in the paper, so that we can have some more high throughput and latency, low latency for that.
Yeah, stage is yours if you have any question or if you want to discuss something.
I did not understand something.
Box full of chocolate. Last.
There is more scope for you.
Okay. Oh, you want some motivation to ask a question? Okay. Here you go.
Yes, Ritesh.
For a part, yes, it is. For like a bit of part, it is doing that work. But after some after some time, like I stated it in the paper, they have only done it for a particular time of tests. Like it was only 15 days, which is like if we do it further, we cannot say that the true randomness are really random because it's the cells are aging and we cannot truly say they're random or not. That's the reason they have done the paper. I think it was the quack one in 2021. Does that answer your question?
But the power dissipation is real, so the randomness is also true. And it is also unpredictable, like how much power it will dissipate or what voltage it will be output for the buffer to get it read from the local row buffer.
Any other questions? Are we going with our questions then? Part of the pipeline. Like they did the procedure again thoroughly. They did the whole they did everything again with like activation the 4 rows and doing that with the DRAM. It was like not just the pre-processing one, it was like the proper pipeline thing.
Not all the time. When the CPU is in idle condition and then only we're using it.
And there is no request coming for bank, process the data, then it activates the D-RaNGe firmware, then it starts with the profiling, and then we use those rows for TRNG. We talk about the critique, the throughput is really high. With 4-row activation, they have high throughput for 2 random number generator, but that will be a bottleneck for the DRAM throughput, the communication with the CPU. So if we have an application like the fitness band that is like frequently connecting with the RM, the CPU and RAM, so it won't generate that much based on the connection request from CPU to the DRAM.
What's the granularity of that randomness, right?
The row will impact the throughput, like quantity of the randomness it will throw, but may not have impact on the randomness. Based on last week presentation, I was also thinking that the DRAM, like a row hammer attack or side channel attack, would be a weakness. But in the paper, they have mentioned the throughput is so high, like 700 MB per second. So if you consider a single bit flipping, they are not considering any attack, or they're not considering that as a security aspect for that because throughput is already high. So okay, so we have our first question. Where does the memory controller store the random bit, like the generated random values? In the memory controller, they store database. Next question. When does the D-RaNGe from firmware is activated, or when it comes to effect for generating the random number? I think we discussed this. Correct. So when the CPU is not communicating with the DRAM, We have, I think, one more question. The strength of cells of each bank differs or remains same with the different manufacturer. Differs based on the manufacturer. Yeah. Shahin. इसमें भी बोला. I think we have one more question. If DRAM can only open one row per bank at a time, what is the advantage of alternating between two rows? Somewhat, yes. Yeah, throughput also and
Both of those mixed.
he's having nut allergy, so at power dissipation level, that is the granularity of the randomness, because the source of randomness is from the power dissipation from the capacitor, and it will take various time for different cells to like amplify for a IO readable voltage. So the granularity would be voltage, the voltage in the capacitor. Yeah, power dissipation, but the voltage level is different. So that's how they have randomness in the row buffer.
Do you have any other questions in the Zoom?
Oh.
So Naeem, maybe feel free to speak up if you want.
Yeah, I think the question was on granularity. Also, I have given two of your answers already. I don't know if how do I get chocolates?
Yeah.
You can just hand them over when we are like leaving from the class.
We have backup of chocolate, so don't worry about it.
You have any other questions for us?
The worry part is randomness, not the chocolates.
So yeah, the granularity was at the voltage level of the cells and how much they require additional voltage to get to the IO readable value. And different cells have different voltage. So if we are reading at a reduced timing of around 45 to 50%, so that's like randomness for the cells to get activated for the local row buffer, and that's how it is creating randomness.
Yeah, the other cells are not in synchronous, right? If you see now, there is no synchronization between other cells now, correct?
Yeah, the
For
cells
other columns. Now given your frequency and the friction and frequency for other cells ranks, I'm not sure how it's gonna impact the randomness for the other cells given
Yeah.
the clock. Yeah.
Yeah, I agree. The cells have dependency on the manufacturer, and they have tried, I think, with 3 different manufacturer, and they have seen randomness in them.
Yeah, I mean we agree, right? So in a single clock, there not all cells are being flashed out, right, with the randomness. So there's
Yeah,
yeah.
you may have 1 to 4 random RNG cells
Mhm.
for
Mhm.
In each bank, there will be RNG cells. That is what.
I see.
And it's totally dependent on the manufacturers and the testings they are doing on the DRAMs, because they have like parameters that were actually dependable. So we cannot say it's truly generating the thing or not. That's also a thing.
Can take chocolate even after the
Can you say something?
Hi, name. No. Yeah.
Hello.
Please answer the question. Right, maybe we have one. Minute.
Oh, after my house. Is there then? I have so because my turn.
Yeah. All right, guys. So I think we're starting now, and so uh, guys. So we don't have chocolate, but we have Starbucks gift card, right? So and we can start now, right?
Online.
Yeah, and the gift cards are we'll have to send email, and it should work. So right, so let's get started.
All right, good. All right, good afternoon, everyone. Welcome to our presentation. I'm Franklin, and this is Trilok. And for our presentation, we chose FlashAttention. So, go back to the previous slide. Yeah. So for our presentation, we chose FlashAttention. Next slide. All right, so let's introduce ourselves. I'm Franklin, and I'm a master's. I'm a master's student at GSU. This is actually my second semester here.
I'm Trilok. I'm a PhD student here, and in research mostly all around. And previously I worked for some time at.
And so for the contents, first we'll start off with the intuition, and then we'll go over our executive summary, and then we'll tell you what is the problem that we're talking about, and then we'll talk about the basics of self-attention and the GPU basics, which will end up being our solution, and then we'll go for the key directions, and then methodology, and then the strength and weakness, and then afterwards the takeaways, and then finally the discussion, the questions at the end. Okay, so let me ask you all a question. So let's picture a picture of a closet so full of clothing that it cannot, that there's no room. You can't fit anymore. It's too overwhelmed. What computer science concept do you think that's related to?
Memory, DRAM.
You cannot understand? Yeah. Okay. Okay. It could relate to like there's so much of memory that you cannot do it anymore. Yeah, but honestly, some of you gave pretty good answers. So let's take a look at another picture. Notice those both pictures show a guy trying to organize papers. So which of these two pictures do you think shows efficiency better? Anyone? So the question was, notice that there are two pictures of a man trying to organize some papers. Like one is doing on like one picture, he's doing it one at a time, and the other he's trying to like organize it into some stats. Which one do you think shows efficiency better? Yeah. Well, that's the second one, but you wearing a suit, that's not the answer. Someone said he's wearing a suit, but that's not the answer. What do you think is the answer? You said the second one, but why? Yes, because because he's able to organize papers into stacks, into organized stacks. So yeah. Yeah, so for the executive summary. Yes, so for the executive summary, so the main problem that we're trying to address is that the standard transformer models struggle with efficiency. And the reason why is because they use a calculation process called attention, and that requires a huge amount of computing power and memory that increases rapidly as the length of a text or a sentence increases. So as the length of a sentence or text increases, the amount of time and memory that it takes to compute the sentence significantly increases, and that makes processing huge, long text slow and resource intensive. And now researchers have tried using approximate attention methods to speed up the time, but however, they actually sacrifice accuracy to gain the speed. And that is a huge trade-off that can affect performance. And so one of the main solutions introduced is FlashAttention. And what it does is that it performs exactly the same calculations as a normal attention mechanism, but it does so much faster than the original attention because it does this by optimizing how data moves within the graph, within the graphics processing unit, which is GPU, instead of constantly moving data between slow main memory, which is labeled HPM, and the fast in-chip memory, which is the SRAM. And it also keeps the entire process within the faster on-chip memory. Yeah, and it reduces input IO bottleneck. And some of the key results for the FlashAttention is that it makes the training and the inference process, the training and inference process 3 times faster without compromising the model's accuracy. And it's also allowed modern LLMs like GPT-3, GPT-4, and Llama 3 to handle large amounts of text at once, which is known as like context length. So moving from a few I wasn't finished. From a few thousand words, like in GPT-3, to even over 1 million words, like Llama 3. All right, next slide. And so this slide displays the transformer neutral network architecture. So you see on the left image, it shows the encoder decoder structure, where encoder processes the input sequence, and then the encode and then the decoder generates the output sequence. So on the encoder, the first text inputs are first converted into numerical representations called embeddings, so the input embedding, and then to account for order of words, the positional encodings are added to the input embeddings, and then afterwards, there's the multi-head attention, and what the multi-head attention does is that it allows the model to weigh importance of different words in the input sequence to each other. And then you have the feed-forward network, which is the feed-forward network is actually a simple full connected neural network, which is applied to each position separately. And then you have the add norm, which is this sub layer right here, so as for the add norm, each sublayer is followed by a a connection add and a layer normalization, which is labeled norm. And what it does is that it helps stabilize and accelerate the training. Now the decoder stack consists of a stack of identical layers, also denoted by the NX, and also the encoder as well. So the decoder layer has some sub-layers. So the first one is the masked multi-head attention. So similar to the encoder's self-attention, it's similar to the encoder's self-attention, but it's actually masked to prevent the decoder from taking in future tokens during training. So to ensure that it generates the output sequentially. And then you have the multi-head attention. Like I said before, this layer helps the decoder to focus on relevant parts, only relevant parts of the encoder's output when generating its own output. And then you have the feed-forward network. The feed-forward network going to add a norm layers, which is just like the encoder has it right here. And then I wasn't done. And so, and so you have the right. So this is the right image. So this image actually illustrates a high-level overview of the transformer encoder and decoder architecture. So on this left side, you have the encoder stack, and so this left part shows a stack of encoders, and what they do, that they process the input sequence. So for example, let's say we input a French phrase right here, and so the encoder wants to build a rich contextual representation of that input sequence. And then on the right-hand side, you have the decoder stack. What they do is that they generate the output sequence, which is the English translation right here. And then you see those arrows right here, they're connecting the encoder to the decoder. So the encoders and decoders are connected, like you see right here, and like I said before, it's indicated by those lines. And what this connection does is that it allows the decoder to focus on, like I said, focus on only relevant parts of the input sequence during the translation process using attention mechanism. So yeah, so just to explain steps. So first, the input sequence is loaded into the encoder stack, and then the encoders process the input. Yeah, the encoders process the input and pass the final representation to the decoders right here, and then the decoders then generates this English translation. Yeah. Okay, so this image right here, it illustrates the concept of attention mechanism, and it's actually a technique that allows the model to focus on specific part of an input data when processing output. So on the bottom right here, X1, X2, X3, and X4, they represent input elements, which are hidden states and outputs from a previous layer in the neutral network. And then on the top, H1, H2, H3, and H4, they represent the output. And you notice those arrows pointing X1, X2, X3, and X4 to H4. They actually represent the current output state, which is basically a weighted combination of all previous input states. So, and you see the equation on the right here. This is actually the this equation right here actually describes the calculation of the attention output. So this is the formula for the attention output. And so xt right here represents the individual hidden states or outputs from the previous layer. And then the SI stands for the attention score. And what the attention score does is that it computes how relevant positions I's output is to the current hidden output. And yeah, so so basically this is the formula for the hidden output. You can go on the next slide. So on this diagram right here, so this tells you the steps. It essentially illustrates the initial steps of self-attention mechanism. So first look at this, those two words, thinking and machines. So first, those two words are converted into numerical representations called embeddings, and they're labeled by X1 and X2. And these the embeddings are actually vectors that capture the semantic meaning, that capture the meaning of the words. And so from here on then, from here, these vectors, so the query's keys and values are computed by multiplying the weight matrices with the embedding. So like the embeddings are multiplied by the query matrix to get the query vector, and then the embeddings are multiplied by the key matrix to get the key vector, and then the embeddings are multiplied by the value matrix to create the value. And the matrices and the matrices so yeah, basically embeddings are multiplied by those matrices to create three separate vectors. Yeah. All right. Yeah, so continuing on from here, so to determine the relevance of thinking and machines, the query vector, which is labeled by Q, is multiplied by the K vector, by the key vector, which is labeled as K, to get the scores. Now notice that one score is higher than the other. What do you think that means? Notice that one score is higher than the other. What do you think that means? No, no, not the car. No, so yeah, quite, yeah, you got it. Anyway, so after this, the scores are then divided by the square root of the dimension of the keys. So this is labeled as the square root of dk right here, and the purpose of the step is to prevent large values from dominating the softmax function. And then afterwards, a softmax function is then applied to these scores right here, and to convert them into probabilities. Now, probabilities, they have to sum up to 1, and these probabilities determine how much of each value vector will be included in the final output. So afterwards, the softmax is then multiplied. Each softmax score actually is then multiplied by the value vectors. So it's multiplied by V1, it's multiplied by V2. And then and then the weighted value, the weighted value vectors are summed. They added up all together to get the final output. So with the output of the self-attention layer for that position. So yeah. Oh, we can go on to the next slide. Okay, so this diagram illustrates the core components of the self-attention mechanism. So matrix. So notice that you have a matrix X. Matrix X matrix X represents the input data, like a sequence of word embedding. So the query matrix is created by multiplying the matrix X by the query weight matrix, and the query matrix represents what is being searched, and then this X matrix is multiplied by the key weight matrix to produce the key vector, not the key vector, but the key matrix, and the key matrix represents the information available, and matrix X is multiplied by the value weight matrix to produce the value matrix. Now the value matrix actually holds the actual content to be extracted and weighted. And you see this formula on the right, and this formula on the right side is the attention formula, which is done by calculating the product of the query, the dot product of Q, the query, and the transverse of the key, and then dividing it by the dot product, and not the dot product, but dividing it by the square root of the dimensions labeled, which is labeled by square root D, and then taking that softmax function, by taking that softmax function. Now this S right here is actually this S right here represents the score matrix, and it's done by taking it's actually done by taking the product of Q and the key and the transverse of the key matrix, like is shown in this formula. And so yeah, and then after I think there's more of that formula. Is there? I think there's more of that formula. Yeah, and then this entire softmax function is multiplied by V, which is the value matrix. And then they're summed up, and this produces the final output. You can. Yeah, that thing fell off. Okay. So this diagram actually illustrates the self-attention mechanism. So let's say we have this sentence. I know it's sideways, but we couldn't find a way to get it horizontal without overflowing the slide. So let's say we process this sentence right here, and so the words on this lower part of the image represent the query, and then the words on this upper part represent the keys. Yeah, the keys and values, the words the model's looking. Okay, and then those lines connecting. So lines connecting word making to all of the so yeah. Okay, so yeah, when let's say it processes the word making, well, those lines pointing the word making to those lines connecting making to some of the words, they represent the attention weights, like how much of 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 a relationship there is. Now, notice that notice that notice that some of the lines are darker, some of the lines are lighter. What do you think that means? Huh? Yeah, yeah. So like the varying. So yeah, some words are more related to making than others. Some words less. Yeah, your answer is actually good. So this diagram illustrates the multi-head self-attention, and which paralyzes the attention layers using a different linear transformations on the input and the output. So let's take a look at this sentence. Let's say that we input this sentence right here. So when you process the word licked in this layer, and then the model places strong attention to the word cat. And so what it does is that it highlights the relationship between the action, which is the word licked, and the object of the sense, which is the word cat. So the cat licked. So, and then of course when you process the word licked in this upper layer, like I said before, it did, and then it also focuses on the word owner right here. What this does is that what this means is that it is considering the relationship between licked and the object, which is owner. So yeah. And what do you think and what do you think the reason for those arrows being much grayer than those two arrows mean? Yeah, yeah. Someone said less related. Yeah, that's right. Okay, and so this and so this slide illustrates the architecture and the process of the multi-head self-attention. So first, at an input matrix labeled X is first fed into the system. Then second, the input X is projected into the multiple sets of query, key, and the value matrices right here. And using different learned weight matrices for each head, which is labeled from 0 to 7 right here. And then and then for each head, right here, a scale dot product attention function is then applied to the respective query, key, and value vectors to produce alpha vector labeled as D. So the way it's done is the product of the query and the transpose of the K vector, and the transpose of the K, the key, and then dividing it by the square root right here of D. Dividing by the square root of the dimension, which is D right here, and then taking softmax of all this, and then multiplying it by the VI, the value, and then afterwards, then the output matrices from all attention head Z0 to Z7 are then constat are then and then concentrated into one single large matrix. So they're converted into one single huge matrix. And then afterwards, I was not done. Then this output is then passed through final linear layer using a weight matrix right here to produce the final output matrix. Yeah. But I'm having some difficulty. Okay, so this diagram right here, it illustrates okay. Oh, I'm having some difficulty. Yeah. Okay. So this diagram illustrates process of computing a standard self-attention to the GPU. So what it does, it starts off with the query matrix, key matrix, and both the dimensions n represents the sequence length. D, yeah, D represents the dimension features. So first, the transpose of the key matrix multiplied by the multiplied by the query matrix to produce an attention scores matrix, which is labeled A. And then afterwards, the attention matrix then is masked. Right here is masked to prevent the tokens from attending to future tokens. So it's labeled by this gray area squares here. And then afterwards, the softmax function is then applied to the attention matrix to obtain the final attention weight. And then finally, the attention weight matrix is then multiplied by the value matrix, which is V right here, to produce the final output, which is labeled O right here. And that output matrix has the same dimension as the query, key, and value matrix. Now, there's some challenges to consider. The first, the attention score matrix can be very large, especially with huge input sequences. Repeated reads and writes from GPU device memory. So what this means is that the process can involve repeated reads and writes to the GPU device memory, which can create a bottleneck, and also the memory requirement and the computational complexity of the intermediate attention scores matrix increases substantially with the square of the sequence length. And that can make it difficult for long input sequence. All right, next slide. Yeah, so this diagram illustrates the GPU memory hierarchy. So this middle picture right here. So this top level organization for parallel execution is a grid, is labeled 0, and this grid is composed of multiple blocks, like block 0, 0, block 1, 0, block 2, 0, and so on. And each block is a set of and then each block is a set of concurrently executing threads that can communicate and synchronize with each other. And on the left side of the image is the per block shared memory. Now, this memory is readable, accessible by all threads in a block. All threads within the same specific block. And its bandwidth is very high right here, but it also has a low, a relatively, it has a small capacity of just 20 MB. And that actually makes it ideal for fast temporary data sharing within the block. And then on the right image is the device global memory. And it's readable and writable, it's accessible actually across the entire GPU. That means all blocks in this grid right here, all blocks in this grid. And it has a much larger capacity. It's 80 gigabytes right here. And its bandwidth is much smaller at only 1.5 GB per second. And this memory is actually for larger database data set and the communication between different blocks. So now let me ask you a question. What do those coordinates mean? 0, 0, 1, 0, 2, 0. What do you think?
They're tiles.
Huh?
They're tiles, right?
What did you say again?
Each of it is mapped to user tiles, and that they are all shader multiprocessors.
This makes sense. Oh, I couldn't hear some of your answers. Yeah, the unique identifiers for the individual thread blocks within the overall grid structure in the GPU programming model. That's what it is. Okay, you can. So you see, so you see on this left image. So this left image right here. So this left image right here details standard attention implementation, the attention algorithm. So first step is to load the query and the keys by block from the HPM. So basically to load the query and the key matrix, and then compute the S. Compute S, which is the product, which is calculated by the product of the query and the transpose of the key matrix, and then you write S to the HPM, to the memory HPM. And then the second step would be to read S, and then you compute the softmax of operation of S to get the P. And then you write the P back to the HPM. And then afterwards, you load the P and then the V, the value matrix, by block into the HPM, which is the memory. Then you compute the output, the final output O. And then you write O into the high, and not write O into the memory. And then this middle image right here, it actually illustrates the flow of data between the memory and the compute unit. So those have multiple layers of memory, which is represented by those blocks right here. And then, and the data moving in, out of the compute block, which is labeled by the arrow. And then right image, and then the right image right here, it illustrates the typical memory in the computing system. So the SRAM is it's fast. It has the highest bandwidth at 19.8 and on 19.8, but 19 EBs per second. There's also the small point, well, at only 20 MB. And then the GPU HBM is right there in the middle. Its bandwidth is 1.5 GB per second, which is much slower than the SRAM, but a lot faster than the main memory, DRAM, and its size is greater than the GPU SRAM at 40 gigabytes, but it's much smaller, than the main. Yeah, smaller than the main memory. And you have this main memory. It's lowest, 12.8 gigabytes per second. Which is less than 1 second. And yeah, that's what it is right here. Okay. So this diagram right here illustrates the concept of tilting, tiling, which is used in computing the attention mechanism. And so, this diagram has three main inputs: the queries, the keys, and the values right here. And those represent the standard components of the attention mechanism in machine learning models. And the main operation, so the central part of this diagram represents calculation of the attention matrix, which is done by multiplying the query by the transpose of K. This matrix is used to compute the final, will be used to compute the final output. And then you notice those blue sections. They actually demonstrate the tilting, not tilting, but tiling approach, as what I meant to say. So instead of calculating the entire large n times n matrix, it breaks down the data, the matrix, into smaller blocks. And then they are loaded, and then those blocks loaded back, loaded block by block, one block at a time, to from the global memory to the faster on chip shared memory for computation. So optimizes the memory access and the speed. And what this method does, that it avoids storing an entire large attention matrix for the memory, and that is beneficial for processing large context and applications like NLP and computer vision, where sequences can actually be really, really long. Okay. Yeah, it's your turn.
All right. Thanks, Franklin. So, right. Can you take over the slide? And yeah. Right. So let's see what are the key directions. Right. So what we saw till now is like how attention is very expensive, right? We see models getting larger, and the demand for better models also getting larger. So earlier we used to process text, but we have models now which process documents, images, audio, and everything. So let's see what are the key directions in this area. So how people solve this problem. So basically, oh, I can have to tap next. Yeah. So the overall research area is efficient transformer, and there are. Oh, I can also. Right. Right. So there are three ways so we can design efficient transformers, right? So when we have a model, so basically there are three things we can optimize. So one is the way we represent the context. The second, can we design a smaller model? And the third, since we saw in the previous slides that attention is the most expensive process because it has O of n square complexity, and it has quadratic time, it increases quadratic times. So with increasing context, so can I design a better linear attention mechanism which can help me make faster inferences? So let's see what first quantization is. So what's basically the idea of quantization is, so let's say I have input which I represent in FP32 or some floating point bit. So can I reduce the number of, so let's say I have 32 bits to represent it. So can I reduce the number of bits that I use to represent that information? So let's say I have int4 or int8 or FP16. So the idea is basically representing the weights and the activations and all the context in lower precision. And so as a result, what we have is, so when we represent the context or the weights of the model in lower precision, so we also have a reduced memory of the complete pipeline. So, but one of the downsides is like most GPUs do not support mixed precision or lower precisions. So yeah. So the second way how researchers also approach this is knowledge distillation. So basically what this is, so can I come up with a smaller model that encodes all the information that a larger model has? So we all have used ChatGPT, and if you have used the API, so basically the GPT-5 mini or the GPT-4o mini is a knowledge distilled version of the larger model. So what happens basically is, so there is a teacher model and there is a student model. So teacher model is usually the larger model, and student model is the smaller model. And usually, people say the GPT-5 size is approximately 400 billion parameters or like 600 billion parameters, but the smaller model is like 20 billion. So you already see that how we reduce the model size with knowledge distillation. But the question is, how do we reduce the model size but still keep the information of the teacher model in the smaller model? So basically, what we try to do is, what we try to do is like something like this. So this is also one of the papers that I've worked. So the idea is basically we have a teacher model and we have a smaller model. So in the time of training, what we try to do is like, let's say I have an input, I make the model I make the teacher model guess or make answer those questions, and I also make the smaller model answer those questions. And but while training, what I try to do is like I try to train or update the weights of only smaller model with this loss. So what happens to the process is the smaller model gets the prediction ability of the larger models. So one of the advantages of this, what we also saw is, so we were basically working with 7 billion parameter models, and the smaller model was 500 million parameter models. At one point of time, so we were able to get better performance with 500 billion parameter model than the teacher model. But of course, this is domain specific, and we can't make domain specific models for everything. So that's the downside. So right, The other thing is the other direction of research, how to make efficient transformer is linear attention. So as we know, as also Franklin presented in the previous slide, what we try to do is like the complexity of attention is O of n square. So can I come up with a method to basically reduce the complexity of from O of n square to O of n? So what they basically so there was a paper like which addressed a linear self attention. So in linear self attention, what happens is like they come up with a matrix which has a lower rank, and so by reducing the rank of a matrix, I can basically reduce the size of the compute, and that's one of the ways I can achieve linear time computation. So these were the three major key directions, and right. So what's the problem with all of these? The one of the major problems is so these are lossy compressions, right? So in quantization, we compress the context, we compress the number of bits, but we sacrifice some accuracy. So these are so these are the approximate attention methods, and what happens is like when the downstream tasks are very difficult, like maybe reasoning or maths, or like difficult problems like bioinformatics, we don't get such accuracy with these approximate attention methods, right? So, and also what happens is like when we make models larger, the errors, the size of errors just amplifies. And right, and one more downside is like so we can't. So since I also mentioned that the model size is increasing and the demand for longer context models is increasing, so these linear attentions don't scale or don't work better for longer context. So as also Franklin mentioned, the Llama 3 model is like 1 million. The GPT Gemini that we use is also people say that it has infinite context. So these approximate attention methods don't usually work, right? So it's very hard to make them general purpose, right? So what is the path ahead? So what we saw is how the compute is expensive, and the approximate methods that we came up with, they do not scale up well, and right, and also sometimes in harder tasks or harder downstream tasks, we see a worse performance, right? So that's why these methods are not widely used. So the idea of the flash attention is like, can we come up with a method which has fast plus exact self attention? So I don't need any approximation, but how can I make GPU and the memory and my algorithm interact each other seamlessly so that I can basically optimize the process? So the beauty of this flash attention paper is the complexity of the algorithm stays same. So at the end, you will see that the complexity of algorithm is still O of n square, but we get faster runtimes. So that's a beauty of this paper. So what we try to do is so there are mainly two main techniques, right? So what we try to do is instead of having or working on a big chunk of matrix, so can I break it down, right? But the problem is, so we'll see the problem. So that's the idea. So can I break the bigger matrix to smaller chunks that I can feed to the GPU, and since the GPU has multiple cores, so each core can process each chunk and come back to me with the final attention matrix. Right. So that's the key idea. But we will see what are the problems when we break down the matrix into smaller chunks. So how the computation changes. Right. So these are the two main techniques that we will be talking about today. So one is the tiling, and one is recomputation. And we'll see with these two methods how we still can come up with this process. Right. So let's come to this again. So mainly attention has 4 steps, right? So one is the matrix multiplication. So let's say I have a query Q and I have a key matrix K. Then first is the matrix multiplication. Then the second is masking. The third is softmax. The fourth is dropout. And then again, we have matrix multiplication. So before coming to optimizing this process, one of the key aspects is to understand what specific part of this process is the most memory intensive, right? So usually, what people would think is matrix multiplication, right? But if you see here, if you see the graph or plot on the right, you can see matrix multiplication has the most lowest time consumption, right? So, but and you see, so what's the maximum time? The operation that's consuming maximum time is basically masking or softmax or dropout. So it's counterintuitive, right? So the operations which are not very math intensive or very compute intensive are taking more time. So let's see why. So this is because, let's revisit this. So basically there are three main parts. So one is the CPU DRAM, and the second is the GPU HPM, and then there's the GPU SRAM. So since SRAM is very small, it is 20 MB, what happens is like at every step, like let's say I calculate the matrix multiplication. So I have the matrix multiplication product, and then I do masking. So basically I have to store this matrix back to HPM. So after every operation, I have to do a round trip to HPM to store the value, right? So that's basically the multiple read and write process between the HPM and the CUDA course is basically the time taking process. And so how can we optimize this? So this is because for when we calculate masking and when we calculate softmax or when we calculate dropout, so basically we have to have access to the complete matrix. Okay, I cannot mask. So let's say I have a smaller chunk of a bigger matrix. I cannot randomly mask any portion. So I have to only mask the information that represents the output, the text that the model has to predict. So in softmax also, I have to average over all the values of the tokens. So that's why I cannot. That's why I cannot calculate, or can I cannot basically calculate the value without having access to the complete matrix, right? So that's why if you see the read and write process, so let's say I have the matmul, so it does the operation and then it writes back. It similarly happens with masking, softmax, and all of this, and that basically is the reason for the time taking. So right. So now we saw that what is the problem, and so breaking down the problem is so there are two major sub-problems. So how do we compute softmax without the entire sequence? So for softmax, I need to average over the entire sequence. So how to compute softmax without the entire sequence, and how to compute the gradients for backprop. So the problem one is solved by tiling, and the second problem is solved by recomputation. So let's see here. So what we try to do is we'll deep dive into this picture, but just on a high level, what this method does is like I can break the key and Q values into smaller blocks, and I can give to each compute block, and then they can compute and come back, and I can basically average over all these smaller values. So let's go a little bit deeper to tiling, and so this will help us understand how we can calculate the softmax. So when I have a set of values, what I basically do, how I basically calculate the softmax is I take the value of maximum value, and then basically I recalculate the value of f of x as you can see that I subtract the value from exponent, and then I sum it over, and then the updated value is the softmax of x is f of x by L of x. So you can see here that how I need access to complete 2n values. So if I break it down to x1 and x2, right? So what I'll have is again I will have a smaller chunk x1 and the smaller chunk x2, and then f of x1 will have some values and f of x2 will have some values, and then L of x1 is the sum of all values in f of x1, and L of x2 is the sum of values of all of x2. But what should have happened is I should calculate all the exponents with respect to max of M1 and M2, because in softmax, basically we scale it with the maximum of all the values in the array. So there is a recalculation trick that in this paper what they introduced. So basically, let's say max of x is M1 and M2. Let's say max of M1 and M2 is M. And so what I can do is, so I have to calculate f of x. And so you can see that how M is broken down to minus M1 plus M1 minus M. And similarly, for values which are calculated with or which are rescaled with M2, so they are again recalculated as minus M2 plus M2 minus M. So if I reorganize, you can see that how I can calculate the softmax for the larger array with by these smaller values also. So the complete idea is like I break down the bigger matrix to smaller chunks, but I still have to rescale each values to the maximum of the complete array. So what the idea is, I will scale. So the idea is I will scale to maximum value. So I will scale each value to the maximum in its compute in its matrix, and then so I'll have these local softmax values. Then at the end, I can basically recalculate the softmax with respect to the max. Then I can recalculate the softmax with respect to the larger M. So that's the idea. So, but the second problem is, so these are never stored in HPM. So these softmax values or these weights values are never stored in HPM. But I need these values while calculating the backward propagation. So what I have to do is I have to, since I have no way, I have to recompute all these values again during back propagation. So what happens is so again I again need to recompute these values. So one of the things that happens in this is the number of flops or the number of floating point operations that I do to process one token increases, right? So this would again, if you feel like this would again increase time, but the main but the main idea is the total floating point operation increases, and but the wall clock time decreases because we had to do multiple round trips to HPM, so which basically slowed down the process, and now we don't need to do that. And we will also see that the number of operations that we are doing per second increases, but still we are not able. So still we are at 30% of the maximum floating point operations that the GPU can do. So that's not a concern for us, right? So again, going over this algorithm and overview. So let's say I have a bigger matrix. I break down into blocks, and I break down. Then I basically do tiling, and for each this matrix and each of these tile matrices given to the smaller cores, and I calculate the smaller values or local values, and I store them. and then at the end, I basically recalculate all these softmax values. Right. So, right. The methodology is done. Now let's see some results. So, right. So the first key thing that you must have seen is we recompute a lot, right? So you can see that in the table on the right, the number of flops increases, but the number of read and write operations to HBM reduces, right? And that's what we wanted. So all of so most of the algorithms that we see in attention are not compute bound, but they are memory bound. So we can do a lot of computation, but we can't do a lot of read and write access with the HBM. So that's why you can also see that in the runtime, that how with FlashAttention we are able to reduce the time required to basically compute or process the text. But one of the disadvantages is like when we have more higher block size, so at some point of time the performance saturates. Right. So this is because like so we are able to divide a larger matrix into blocks, but when we also increase the number of blocks, so that's limited by the number of cores that we would have. So it's not that like we could also increase the number of blocks that we divide a matrix into. So right. So why is this effective? Because all the previous papers, so they addressed attention not in tandem with the GPU architecture. So they try to modify, or they try to come up with approximate methods to go to calculate attention. But here, so this was the first paper which basically designed a method so that like we could have memory efficient exact attention. So all the key findings they just put in the title itself. So right, so SRAM is much faster than HBM, so do as much compute while inputs is there in SRAM, and moving things around SRAM is very cheap, and right. So oh okay, right. So right, so we saw that the training speed has increased, right? And so this is one of the benchmarks where we see the training speed has increased, and right, this is again, and so this is also a long arena benchmark, which basically says that how we are able to replicate, or we are performing better than approximate attention methods with higher speed up. The one more, so this is an important takeaway. So let's say I have a budget of like 100K to buy a GPU or build a data center. So with that similar budget, I can train a model which has longer context length, and this is what we wanted, right? So training time wise, FlashAttention with 4K context is higher, and we have better perplexity. So this is not surprising because this is not approximate attention. This is accurate. So the takeaway is like for same time budget, FlashAttention allows training of a better model. Right. But again, like at some point of time, this breaks. Linear attention time. So the crossover points are basically where linear attention crosses this. Because of course, linear attention would, so we are not reducing the complexity of algorithm as I mentioned. So at some point of time, the linear attention perform better, but we know that that's a cost of accuracy. Right. So there are some strengths. So I have to repeat the training time speed up, and the faster adoption. It's readily available with many open source libraries. But one of the main weaknesses is like, so let's say I release, so the Jensen announces a new architecture tomorrow. So we'll have to again write a new library for this. So it's very GPU dependent because I'll have to rewrite the CUDA kernels so that I can manipulate the SRAM to HBM memory transfers. Right. Right. But there is one more important thing. We did a lot of things, but this doesn't speed up inference, right? It's because we also have to do KV cache optimization, and we also have to do faster decoding. So I think KV cache was presented last time. But we are able to increase the training time. But in practice, also, so in the paper talked about a lot that we are able to get faster inference times and running time, faster running time, sorry. But this doesn't scale up with model families. So Mistral is a very popular model family, and you can see that there are a lot of complaints that this doesn't work for Mistral. And there's also a GPU series RTX 509 Pro. It doesn't scale up really well. So these are real GitHub issues, which I pulled off and put it here. And right. The takeaway is like we don't change the math, and attention is bottlenecked by memory, not by compute. And right, we do tiling to increase. And yeah, so there were more. So one thing I mentioned is like we are compute bound. So the FlashAttention is still able to use 30% of the maximum flops that H100 can achieve. So of course we need, so the future directions are faster and more parallel attention. And again, like we also need to increase it to, yeah.
Pretty much it for our presentation.
Right.
So I have a question, right?
I'll get you in we'll get you in a moment, okay?
Yeah, this so quantization doesn't change the, so we still do the same thing, right? But let's say, so this was a simple example that you gave, right? But we have more complicated downstream tasks like that I mentioned, like reasoning and all of this. So it doesn't perform that well, right? Yeah. But you saw, right, with same time budget, I can encode higher precision numbers, right? Right. So with higher precision, I can get good accuracy. So quantization does reduce the number of bits, but in FlashAttention, I need not reduce bits. Yeah, yeah. Right. So this we still reduce a lot of. So when we reduce a bit, we reduce a lot of information, right? So maybe the relation and the example that you gave. So there are more contexts that can be preserved in a 32-bit rather than a 8-bit, right? Right. Right. Right.
So someone in Zoom had a question?
Oh,
Amy, you have a question, right?
Yeah. Can you hear me? Hello.
yeah.
Yeah, I think the packing back in is happening in GPU or CPU. If it is happening in CPU, right, then that's an overhead. If it is happening in GPU, then you have more instruction to do repacking, isn't it?
No, the packing, you mean like combining the whole matrix and everything?
Yeah, yeah, the
No,
split.
no, no. That's happening everything in HPM and SRAM.
Okay, it's all GPU business. Now
Yeah.
you've got more instructions to do that, right?
Yeah.
So that's an instruction overhead. Like, did that had any implication on performance?
So I think so I already mentioned, right? So we can process more instructions. So we can but
The bottleneck is memory, you're saying, and that you can
Yeah.
hide compute latency, huh?
yeah. So
Yes.
so the bottleneck was the round trips that we had to make between
The amount of time that the memory that it took to
yeah
transfer data from one memory type to another.
when we are processing long matrices.
I see. The other question was how is the compute happening, right? Is it on native FP32 or the quantized data?
So right. So I also presented, right? I think it's the same question. So so they use FP32 because they can so all of their results they didn't reduce the precision because they wanted to show that that with the same compute budget and with the same precision we can achieve faster faster compute and without loss to accuracy.
But you said we have quantization in place, right?
Now, quantization is one of the key directions that researchers took
I
earlier
see. I
to
see.
make efficient. Processing.
Okay, I see.
Right, right. We are over time, but we had some questions which had Starbucks gift cards. So
It's online.
so yeah, but
But we're not getting it in class. It's online. We'll have to
email you. Yeah.
They must be through the program.
Yeah. Right. So yeah, these are easy questions and what's the complexity and sorry? Yeah. Right. Yeah. Yeah. So the next question is like, so why can't standard PyTorch or TensorFlow implement FlashAttention by itself? And it's depend on type of GPU.
Because it is tightly packed with GPU information, right? You need those underlying information, and that doesn't have covered in PyTorch TensorFlow.
Yeah, actually, so we have to rewrite the CUDA kernels
Correct.
to access or like to manage the transfer of data. So so for CUDA kernels, like we have to rewrite in CUDA or Python or something, right? So I think Naeem, yeah.
What? Yeah. So what's the process of tiling?
Oh, yeah. Right.
Okay.
Yeah.
You remember the first lecture, first talk? We forgot to stop the live streaming and went forever. I think it was 14 hours or so. I have to trim it at some point. Guys, don't forget to nominate the best talk for today. Okay, please send email as soon as possible. Hey, me just stop this.